project is exploring the clinical application of vision transformers. So we know how ChatGPT with language that really blew up and was when the general population really started taking notice. And we thought to experiment with generalizing the architecture to see how well it does on images. I'm James, going to fourth year next year.
Peter, I'm at Unimel, going into first year med.
Yeah. And I'm Jeff, and I just graduated this year from Monash.
Okay, so I'll start by just taking you guys through a little bit through the whirlwind of transformers and how we ended up with vision transformers. So pretty much, transformers were this really revolutionary thing in 2017 from this paper, the attention is all you need thing. That's really been cast up in lights, and essentially it's just a neural network with this thing called attention, which is what allows us to. It's a mathematical trick that allows us to basically handle sequential data really well. So in terms of, like, let's say you've got a sentence, being able to have different words in the sentence in context, being able to infer meaning from each other is really important. But then a couple of folks at Google actually sort of realized that this idea of like breaking up words into like mathematical representations, like a list of numbers, and then getting them to infer context from each other, some folks at Google realized that like this concept can actually be generalized to other modalities and different forms of data that doesn't necessarily need to be just words. So that's where we sort of start thinking, okay, we go beyond language and we think, okay, maybe we can like look at images or videos or other types of data as these as sequential data, and then thinking, okay, we can actually like break this up in some way. So in our context, right, we have an image, and what we essentially do is we have this large image, this cat, and then we break that down into smaller patches. So each square becomes like a little patch, a little segment of that image, essentially. And then each of those images, right, imagine that square is like this, right? We can actually turn this matrix, we flatten that down into a vector, and then that becomes like, that becomes the equivalent of like a word in our sentence. And that's basically the idea of how we can break down the images and then turn them into things that look like words, and then infer context from them and get a better understanding of images, right? And this is just like is it working? Okay, great. This is like a sort of like animation of the vision transformer architecture. It basically just starts off with those patches, as I said before, turns them into some mathematical vector representation, and then passes them through the normal transformer model. But I think what's like actually important is, like, why are we doing this? Because I think, generally speaking, medicine is a highly multimodal field. Like even when we in medical education, it's always, it's not just anatomy, it's not just physiology. You need pathology, you need biochem, you need to put all of these, you need pharmacology, you need to put all of these different elements together to really get a unified understanding of medicine. And I think at the same time, when it comes to gathering data in order to make good models, you also need to have lots of different modalities. Like you might need genomics, you might need proteomics, transcriptomics, you might need history taking, like EMR, imaging as well. So what we're sort of thinking is, okay, how can we use this new technology that's come out and actually start trying to adapt it to different modalities, so that eventually we can actually build something that is like a model that can really generalize across all of these different fields, and in that way make the most informed sort of diagnosis. So that was the goal, essentially, what we're doing, and then James will talk about the model that we've built.
So this is trying to classify cardiac hypertrophy using chest X-ray. We're going to talk about clinical snippets in a second, but you can see that first try, we got 86% accuracy. Crazy, right? But then we looked into it more. Literally first try, we're like, oh shit, we're doing so well. sorry. And then because like computer science bro might be like, okay, you know what, that's pretty good. We can sell it to some people. But we looked a bit deeper. So because only 86% of people have normal chest X-ray, so the model's like, okay, if I guess everyone has normal, that means that I'll get a specificity of 100 and a sensitivity of 0. And then at the time, I was like, okay, that's good enough. So, we tried to run this through because we had a skewed data set where most people don't have the label that we're trying to predict. So we had to do a lot more tricks. For example, using the X-rays, we're trying to augment a little bit using some algorithms that basically give it more training sample. And also because our positive labels are significantly less, there's significantly less of it. When we train it, we try to sample more of that. So essentially, we're trying to create a balanced data set, so the model can't just go like, I'm happy enough with 86%. We can just classify everyone as perfectly fine. So that's what we did. And then throughout the way, we tried to experiment with tons and tons and tons of just like these hyperparameters, and we learned a lot during that process.
We're still going. The model's still
running.
We're
literally
we're still training it.
We got really close. So you have to talk about the result. We got really close to the original paper, but a couple more days and we can definitely beat it. Anyways.
Okay. Yeah, sure. So we have two projects. The first one is classifying cardiomegaly from chest x-rays and echocardiographic data. So make sure we're on the same page. So we're talking about heart failure, which is a complex clinical syndrome with symptoms and signs that result from any structural or functional impairment of ventricular filling or ejection of blood. So it's becoming increasingly clear that early detection of heart failure, or at least structural changes within the heart, can improve long-term outcomes for patients with heart failure. And that's proven from the Oxvalve study in 2016, which is a massive echocardiographic-based population screening cohort study, along with other clinical trials. And it showed that the earlier we pick up heart failure, the better patients tend to turn out. However, that is a challenge because in the early stages of heart failure, patient symptoms and signs are often quite non-specific and can often be referred to as deconditioning or simply aging. And I'll refer to the 2022 AHA-ACC guidelines to examine how they have structured the stages of heart failure. And what we're interested in here is stage A and stage B of heart failure. So that's what we're looking at. Why? Because we can actually make a difference and treat these patients if we pick them up early enough. We can optimize their blood pressure with antihypertensives. If their LVEFs drop below a certain level, we can start them on guidelines-directed medical therapy and optimize their cardiovascular risk factors with more and more medications that we have. So hopefully we've convinced you why it is important. So the tools we need to screen for early heart failure has to be a tool that is accurate, broadly applicable, and cost-effective. We have two options. First are echoes, echocardiograms. They are gold standard, but the patients who do receive them are a narrow cohort who are receiving echoes because they are at high pre-test probabilities. So using using Bayesian reasoning, we can understand why they're getting these investigative tests, which can be quite expensive. And on the other hand, we have chest x-rays, which are inexpensive and incredibly accessible. So what we have done here in our model, in our visual transformer, is to take 3 echocardiographic measurements. The first one is left ventricular posterior wall distance. The second one is interventricular septum distance. And the third one is left ventricular internal diameter and diastole to predict 2 labels. The first 2 would predict severe left ventricular hypertrophy, and the third would predict dilated left ventricle. And the thresholds we used to make these diagnoses for these binary labels are in accordance to international guidelines. So what do we find out? Well, and how do we achieve this? We imported a vision transformer from Google Hugging Face, and we trained it on many chest x-rays and many patients. And this is what we got. This is our receiver operating characteristic curve. And at one stage, we got up to the AUC of 0.75, which is around what the original paper got, but given the restraints we had in the number of epochs we could run, this is what we have currently, which is still pretty good. And this has already outperformed 15 board-certified radiologists in predicting cardiomegaly with chest x-ray. So given we only started this model for a few days, I think that's a pretty good result.
We got the data on like Wednesday, so we got the data on Wednesday.
Wednesday, so we trained it for how many days? For like 2 days, and we did better than radiologists. But
it got up to 0.78 at one stage. I didn't say it because I thought I could do better.
Yeah.
I didn't do better.
Yeah. So that's why it's still being trained. It's still training right now on one of the computers. So we'll see how far it goes. And our second project relates to aortic stenosis severity classification from echocardiograms. So we know that aortic stenosis is a very important condition. It affects 12.6 million adults worldwide, and every year it's responsible for 125,000 annual deaths. And once again, referring back to the 2016 Oxvalve population cohort study, it shows that a lot of these aortic stenosis patients are undertreated and under-recognized. And in fact, when we look at the 2021 Journal of American Cardiology State of the Art Review, we see that all phenotypes of aortic stenosis patients are undertreated, especially in paradoxical low flow, low gradient aortic stenosis, where only 32% of patients are receiving life-saving aortic valve replacements. So why is this important? Well, we want to pick up these patients early. And why? Because these patients, when picked up at an early stage, is very critical and can synergize very well with ongoing commercial efforts to develop therapeutic targets for calcific aortic stenosis, which, as we know now, can only be treated surgically with no medication or pharmacological options available. And part of that reason is we don't have enough patients in clinical trials who are at early stages of aortic stenosis. But why do we need imaging? Can we do clinical diagnosis of aortic stenosis? Well, not really, because again, symptoms are very non-specific, and on auscultation, trials have shown that general practitioners have around a 40% sensitivity in picking up AS with 60% specificity, and cardiologists unfortunately don't do that much better with only around 30% sensitivity, so even less than general practitioners at cardiac auscultation. So we are looking at using echoes to grade aortic stenosis, and the reason why we've chosen to use echoes is because echocardiograms as a screening tool for the population can be prohibitively expensive and inaccessible, in particular for patients in resource poor areas or rural areas. But as point of care ultrasound has become more and more mainstream, and hopefully with better and better equipped images, I think automated interpretation of aortic stenosis severity grading can be achieved, especially because the key features needed for aortic stenosis grading can all be picked up on a 2D image, such as valve thickness and the degree of calcification.
So I just want to take you through briefly through the approach that we went with for this, because given the fact that we're working with echoes now rather than chest x-rays as we were in the previous project, the data modality has changed. So at first we were working with images, but now we're working as videos. So an important question is, okay, how do we actually adopt the models architecture in order to take in videos? Because we can look at a video as just like a batch of images, right? So just a bunch of images in sequence that are happening. And so in that sense, we can just, okay, we just say, sure, we'll just pass in each individual image to the video. We just use the same pre-trained model that we did for the chest x-rays, and then that'll all be all fine. But then an eminent problem with this is that when you think about a video, right, like each frame flows onto the next, and like there is context that is embedded within the video, right? Like what happened at the start of the video is not going to be the same as what happened at the end of the video, and things that are happening in the middle will affect things that happen later, especially if you're looking at like a heart beating, for example. So we needed to come up with some sort of architectural method to take care of this and ensure that like the model is adequately able to deal with echo data, given that it's video. So it basically what we do is we turn each of these each echo into a batch of images, but then basically we add in a few extra aspects to the model. So initially with the normal transformer, we're taking in sequences of words, and what we want to do is, and in this case images, right? We want to basically say, okay, this word is the first word in the sentence. This word is the second word in the sentence. This word is the third word in the sentence. That's called a positional encoding, and that basically tells the computer, like, okay, this is the start of the sentence, this is the end of the sentence. So it knows where it is. And essentially, we have a similar thing with images. We say, okay, this is at the top left of the image. Here's like second row on the right. Here's the bottom right corner. Here's the middle, right? That's called that's sort of like a positional encoding for the image. That's what really helped us with the chest x-rays. But now we have an additional problem, because now the computer's got to say, okay, where am I in the image? But also, where am I in the video, right? Because they're two different things. So that's what brings about this idea of what's called a temporal encoding. It's what I term it. I don't know if it's actually a term. That's just what I call it. But anyway, temporal encoding is essentially just saying, okay, this is the first frame in the video, and all the numbers that deal with that first image get an additional encoding to say your image 1, and then all the guys that are dealing with image 5 will say, okay, your image 5, and then that way the computer knows like which part of the echo, which part of the video is it actually dealing with, and then it can essentially allow these different components of the video to attend to each other, so to speak, or to derive context and meaning from each other. So that's essentially the idea that we were working on with the videos. It is obviously pretty experimental. We only sort of just started this, and also one thing is that we had a lot of problems with data sourcing, like immense problems. It's not even funny. Like it was just ridiculous because we originally tried to get echo data from PhysioNet, which is an MIT Harvard affiliated database, and they gave us 1.7 terabytes of echoes from about 500,000 patients. We're like, oh my god, this is amazing. We're going to build the best vision transformer ever. It's going to be a genius, right? And then no labels, so we couldn't train. Like we basically had a bunch of images, but we didn't know what any of it was. So we couldn't train a model on it because we thought we were going to have cardiologist reports, which would have been really amazing. But then they were like, nah, we're actually still uploading them, so we haven't got them to you guys yet. So just hold tight, and we'll say we've got like 3 days. so what ended up happening was we had this aortic stenosis data instead, but the problem was that they were only very small, 112 by 112 images, which was highly compressed, which was great because it meant that we didn't have to spend 10 grand trying to train the model. That was wonderful, but also we had limited data and limited pixel sort of size. So anyway, in terms of our preliminary results from like yesterday, we think it's okay, but we found that it tended to classify a lot of patients as just having severe or significant aortic stenosis, and I think that is just a reflection of the data set that we were given in the sense that like 75 to 80% of the data set that we were given was just severe aortic stenosis patients, which I hope is not really a reflection of the Australian population. I don't know, Jeff can probably tell better than me is in the clinical setting, but so we tend to notice that the data, the model seemed to overfit to that aspect of the data, which is understandable given the data set size. But yeah, we hope to obtain more data. Hopefully from some guys at Victorian Heart Hospital, maybe if they're open to sharing their data with us. I don't know. We'll see. Anyone that's got good echoes, just send Jeff an email.
Labeled echoes.
Labeled echoes, so we can actually train a model. But we'd really like to eventually combine these echoes, not just with like aortic stenosis labels, right? So this one was just like, we have an echo and then we have a label: severe, no aortic stenosis, moderate aortic stenosis. But we'd actually like a full cardiologist report, so that then we can really enhance the granularity of the output that the model can give us. I.e., here's an echo, derived not just aortic stenosis. No one cares. Let's get the whole report. Let's get everything that we possibly can. But to do that, we need a significant amount of echoes and also the actual labels, which would be reports. So that's where we're hoping to take it.
Yeah, so things that we've learned, and honestly, like the main challenge wasn't even the model. We literally could only start training like 2 days ago. But in terms of, we went along a long journey, like all the way from medical students to proper developers. We started with Colab, and you can just open a web page right now and start coding Python. It's amazing. And Google Drive as well to store our things, but then it took way too long. So we thought, okay, there's a pro version of Google, right? So Google Cloud for the computers and Google Enterprise for people who actually train this code, but it still just took way too long. Like the problem was even the GPU at that point. It was just how long it takes to get the information from the cloud. And uploading the cloud was another story in itself.
Buckets.
Yeah, buckets. It's called buckets, not folders, yeah. And blobs are the things inside the buckets. Why? And then we got virtual machines. So we literally grabbed a little slice from Google's machine, and we literally had to go around like 20 different places because like surely you would think the whole country of Australia would have one of the worst GPUs for us to use. But we went from like Europe to, and we got some at Warsaw. Like
Warsaw was good.
Warsaw was great. Nothing in America.
Shout out to the Polish mates over there. We got a great GPU.
Okay, so we tried like 10 different places, and eventually we got a GPU for us. And then, so at that point, like it was like really bad. So it took 8 hours per 70,000 X-rays, which is like ridiculously bad, especially since we had 2 days to train it. So we thought, okay, how can we like go into the virtual machine to like make it better? So it took us on a journey. So firewalls, how to get to the virtual machine in the first place, all the protocols and port forwarding. And then this is the worst part. This is 1,000 lines of red text. And I have to find 3 lines in here to change like 3 different lines. And then you can't even scroll Control F. You just have to scroll through 1,000 lines.
No, and then I spent 10 minutes on it, and then I ran it to try and run my notebook, and it's like, oh, you have an indentation error somewhere. Go fix it. It's like, where's the indentation error?
There's
Where am I
one
gonna
space
find
somewhere,
it?
yeah, one space somewhere here.
It was very frustrating, but worthwhile.
And then there's no buttons to click because of virtual machine, so we had to like do it all from the command line.
Hacker time.
And then like to open this something, we had to drive with no laptop, allow origin, like it just, and then yes, this is how commands. But it was very rewarding at the end because we will see that, oh wow, we got 16 gigs of GPU RAM and we're using most of it. We try to use as much as possible. So in the end, we actually got from 8 hours per epoch to 7 minutes, which is like pretty, like yeah. If we have more time, like we can definitely beat. So the original paper was 0.8 error under curve. We got really close, but yeah, just I think more time and.
The
Quick
original
data
paper
access.
ran for 50 epochs. How many epochs did we run?
Like this is like 2.5.
So we think we do think there's definitely potential in this field, but we'd be really open and receptive to any other ideas or clinical applications of this sort of architecture, and then we'd like to see how well it would scale with larger models, especially and more compute, and especially now that we know like how to fast track and get to the right computer at the right time. Because like for example, we had 70,000 images, and on the website they just give you a folder with 70,000 images, and we were like, okay, let's just upload it to Google Drive, that'll be fine.
It crashed.
It just crashed my computer because like Google Drive can't handle it. So we need like we needed to go more low level. So now we know what to do.
Yeah, and also just something interesting. This is more proof of concept to see how the architecture would go, because like the original is optimized not for classifying images. It's literally like trying to tell a cat is a cat or like a building's a building. So if we have more time as well, we would like to train our own chest X-ray specific foundation model, but that will be like quite expensive as well.
All right.
Thanks guys.